Hi friends, welcome to a new video lecture of our crash program or revision program of physics for NEET and JEE Unit 7 Gravitation. This topic we are starting with Newton's law of gravitation. What is Newton's law? Two masses m1 and m2 whose centers are separated by a distance small r, then the gravitational force acting between them is given by the equation F equal to G m1 m2 by r square, where G is called a universal gravitational constant whose value is given by 6.67 into 10 power minus 11 Newton meter square kilogram power minus 2 and 6.67 into 10 power minus 8 dyne centimeter square gram power minus 2. Value of G is calculated by Henry, Cavendish, and from here we can say its unit easily because G equal to Fr square by m1 m2, so Newton meter square kilogram power minus 2. This is the SI value, and 6.67 into 10 power minus 8 dyne centimeter square gram power minus 2 is the CGS value of universal gravitational constant. Force due to m1. Force due to m1 on m2, I am giving it as F12. Force due to m1 on to F12 equal to, we can say, G m1 m2 by r12 square, but force is vector quantity. Force is vector quantity, so we have to represent a unit vector here to show the direction of force. Force due to m1 on m2, what happened? Force due to m1 on m2 is towards m1. This is F12 towards m1. m1 attracts m2 towards it. Then what is the displacement vector? Displacement vector is r12. It is calculated from m1 to 2 because m1 is providing the attraction force and it provides force towards it. Okay, so we have to give unit vector r12 minus negative of unit vector r12 because m1 attracts m2 towards it. So displacement vector is away from m1, that means towards m2, and the force is from m2 towards m1. So this is the vector form of gravitational force, and we can change this form into vector F12 equal to minus gm1 m2 by r12 square into vector r12 divided by r12. So minus gm1 m2 by r12 cube into vector r12, because we know that every vector A equal to its magnitude and unit vector. Vector A we can write as its magnitude and unit vector. So unit vector equal to vector A by magnitude of vector A. So r cap means vector r by its magnitude, its modulus. So you will get gm1 m2 by r12 cube into r12 vector. Negative represents gravitational force is always attractive. Force due to m1 on m2 is towards m1. Okay, like that at the same time m2 attracts m1 towards it. What is the direction of force due to m2 on m1? Force due to m2 on m1 is just opposite of F12, vector F21. So we can say force due to m1 on m2 is action and force due to M2 on M1 is reaction. Here there is an action-reaction pair. So we can say Newton's law of gravitation obeys Newton's third law of motion. To every action there is an equal and opposite reaction, and they will not cancel each other because they act on different bodies. For a body on Earth's surface, gravitational force acting on it is Gmm by r square. That gravitational force is the reason for the weight of the body. So we can equate that force to the weight mg. So mm cancels, then we will get G equal to acceleration due to gravity equal to Gm by r square. By giving the value of G, m and r, G value we already discussed, and what is the mass of Earth? Mass of Earth is around 6 into 10 power 24 kilogram, and radius of Earth is 6400 kilometer, or we can write 6.4 into 10 power 6 meter. By giving these values here, we will get value of G as 9.8 meter per second square in SI, 980 centimeter per second square in CGS, and 32 feet per second square in FPS. G equal to G into what is mass? Mass is volume into density. Volume into density. Density equal to mass by volume. Then mass equal to volume into density. So G into for Earth volume is 4 by 3 pi r cube if it is considered as a uniform solid sphere, into density rho divided by r square. So 1 r will cancel. Small g equal to, we will get 4 by 3 pi r rho g. 4 by 3 pi r rho g. So for g we have two equations, Gm by r square and 4 by 3 pi r rho g, where rho is the density of Earth, average density of Earth. So rho equal to, we will get an equation 3g by 4 pi capital Rg. By giving all these values, we will get average density of Earth equal to 5.5 into 10 power 3 kilogram per meter cube. And this is the equation to find average density of Earth. Here is a question. If the radius of Earth were to shrink by 1%, its mass remaining the same, the acceleration due to gravity on the Earth's surface would, options are decrease by 2%, remain unchanged, increase by 2%, increase by 1%. Just to pause the video and try to solve it. Here, radius decreases by 1%. If radius decreases and mass remaining the same, mass does not change, right? So what happens? G increases. G increases. How many percent? We can say it is 2%. Why? We know that equation of G equal to Gm by r square. Here mass is constant and radius decreases by 1%. So as we did in the case of error analysis, we can say delta G by G equal to 2 into delta R by R. If radius decreases, G increases, and if radius increases, G decreases, because R radius comes on denominator. Okay, so here is the answer. The answer is option C, increase by 2%. Next heading, variation of G. Okay, how G varies. First point, due to shape of Earth. Due to shape of Earth, we know that shape of Earth is oblate spheroid. That means flattened at poles and bulged out at the equator. So we can say equatorial radius is greater than polar radius. We know that G equal to Gm by r square. So G at equator is less than acceleration due to gravity at poles. G at equator is less than acceleration due to gravity at poles. So we can say G at poles, by giving the correct values we will get G at poles equal to G at equator plus 0.018 meter per second square. Here is a question. Where will it profitable to purchase 1 kilogram sugar by spring balance? At poles, at equator, at 45 degree latitude, at 40 degree latitude. What is your answer? For buying 1 kilogram sugar, 1 kilogram rice, whatever it may be, it is profitable buying it at poles or at equator. That means where the quantity of sugar is large, at equator or at poles. Answer is option B, because at equator weight is small than at poles, so its volume will be large. So you will get large volume of sugar of 1 kilogram at equator than at poles. Option B is the right answer. Second one, variation of G with height or with altitude h. Okay, that means here we are discussing outside the earth condition, above from the surface, above from the surface. So we can say distance of the point from the center is small r. Distance of the point from the center of earth is small r. That small r equal to what? Capital R plus h. Small r equal to capital R plus h. Small r always indicates distance from the center of earth. Small r always indicates distance from the center of earth. So G dash with the height equation is Gm by small r square. G dash with the height equation is Gm by small r square. Small r will come instead of capital R radius. Okay, that is the distance of the point from the center of earth. So this equation we can rewrite as capital Gm, we can write G capital R, G capital R square divided by, and small r we can write capital R plus h whole square. This is acceleration due to gravity with the height. Okay, if height is negligible when comparing with the radius of earth, then applying binomial theorem, we will get G dash with the height equal to G into 1 minus 2h by r. G dash with the height equal to G into 1 minus 2h by r. But this equation is applicable for small height only. For very small heights, we can apply G dash equal to G into 1 minus 2h by r. Otherwise, in all cases, you can apply G dash with the height equal to Gm by r square or G r square by r plus h whole square. So, we can discuss a question here. If height of a body increases to 6,400 kilometer, that is equal to radius of earth. If a body is raised to a height 6,400 kilometer equal to radius of earth, then what will be the acceleration due to gravity acting on it? How can we calculate? We can take this equation or here G dash with the height equal to what? Small g r square by r plus h whole square, h equal to what? R. So we can say 2r whole square on denominator, r plus h, 2r whole square. So we will get r square cancelled, then we will g by 4. 1/4 of acceleration due to gravity on the surface will be at a height equal to radius of Earth. Here we can discuss one more question. If height h equal to r, then acceleration due to gravity equal to g by 4. Then what will be the height when acceleration due to gravity equal to g by 2? When g dash with height equal to g by 2, then what will be the height or what will be the altitude? How can we calculate? We can use the same equation. Instead of g dash with height, we can give g by 2. So we will get g by 2 equal to g into r by r plus h whole square. We used the same equation. G into r by r plus h the whole square. We have to calculate h. G cancelled. By taking square root, we will get 1 by root 2 equal to r by r plus h. Okay. R plus h equal to root 2r. R plus h equal to root 2r. Then h equal to what? Root 2r minus r. So we can write root 2 minus 1 into r. This is the height when acceleration due to gravity is half of its value at the surface. Root 2 is 1.414. Then we can say 0.414 r. 0.414 r is around, by calculating we will get around 2650 kilometer. 2650 kilometer. This is the height when acceleration due to gravity becomes half of its value on the surface. Third point, variation of g with depth, small d. With the depth means inside the earth. Inside the earth. You can see the diagram. At a depth d from the surface, but d is taken from the surface and small r distance is taken from the center. So what was the equation? G dash with the depth equal to g into 1 minus d by r. This equation we can use in all conditions. Here there is no any condition if d is very less than r. It is applicable only when height is very small. Then we will use the equation g dash equal to g into 1 minus 2h by r. For that equation only we will use the condition. We have to use the condition height is very small. Here there is no such conditions. So g dash with the depth equal to g into 1 minus d by r. And here we can say g into r minus d by capital R. R minus d is small r, distance from the center. So we can say g dash with depth equal to what? G small r by capital R. G small r by capital R, or g dash with depth equal to, we can write what? Small g, gm by r square. So we will get gm by r square into r cube into small r. Gm by r square r cube into small r. Okay. So here you can say g dash with depth proportional to r, directly proportional to r, and g dash with height directly proportional to, g dash with height directly proportional to 1 by distance square, as we discussed in the earlier case. So what will be the acceleration due to gravity at the center of earth? At the center of earth, small r distance equal to, distance from the center equal to 0. So g dash with the depth equal to 0. So at center of earth, weight of every body is 0. So we can say every body feels weightlessness at the center. Every body feels weightlessness at the center of earth. Next, variation of g with rotation of earth. As earth rotates, particles on the surface gets weight mg inwards towards the center of earth, and a centrifugal force away from the center of earth. So body experiences two types of forces at the same time. Okay, so we can say the resultant force on the body or apparent weight of the body equal to actual weight minus centrifugal force due to rotation. Actual weight minus centrifugal force due to rotation. With that centrifugal force, every body on Earth's surface tends to fall away from the earth, tends to move away from the earth due to that centrifugal force. Apparent weight, we can give the equation mg dash, and actual weight is mg. That centrifugal force due to earth's rotation is given by the equation mr omega square cos square lambda. This is the centrifugal force of a body on Earth's surface, mr omega square cos square lambda, due to Earth's rotation about its own axis. Then m we can cancel out. G dash equal to what? G minus r omega square cos square lambda, where r is the radius of Earth, omega is the angular velocity of Earth's rotation. That omega we can find it to pi by t. Okay, time period is 24 hours. Okay, by giving that value you will get omega. And what is lambda? Lambda is the latitude. Lambda is the latitude. Latitude at poles. At poles, lambda equal to 90 degree. At poles, lambda equal to 90 degree. So we will get cos 90 is 0. So we will get G dash equal to G. G at poles equal to G, because axis of rotation passes through the poles. So poles remain at rest when Earth rotates about its own axis. So at poles, weight of a body is not affected by Earth's rotation. And what is the weight of body or acceleration due to gravity at equator? At equator, lambda equal to 0 degree. So we can say G at equator equal to G minus r omega square. Effect of rotation is maximum at the equator. And by giving value of omega and radius of Earth, we will get r omega square as 0.034 meter per second square. R omega square equal to 0.034 meter per second square. The value is very small, but there is a change due to rotation of Earth at the equator. So we can say, as the body goes from equator to poles, as the body goes from equator to poles, what happens? Lambda, latitude increases. Latitude increases. As latitude increases, effect of rotation decreases. Effect of rotation decreases. So G increases. G increases. Weight of every body increases as it goes towards poles. So increase in or change in acceleration due to gravity at poles is due to two factors. One, due to rotation of Earth, and two, due to the shape of Earth that we discussed as first case, variation of G. So we can say G at poles equal to G at equator plus 0.018 meter per second square plus 0.034 meter per second square. Okay, this is the value of acceleration due to gravity at poles. Then we can say, as speed of Earth increases, as speed of rotation of Earth increases, the centrifugal force increases, so acceleration due to gravity decreases, and weight of a body on Earth's surface decreases except at poles, because there is no effect of rotation at the poles. And when the body speed of a body increases to a particular value, then what happens to the weight of a body? Weight of a body becomes zero and the body just fly off from Earth's surface. What will be that speed and what will be that time period? So I am here calculating that time period of Earth's rotation. Time period of Earth's rotation when Earth's rotation, when weight at equator becomes zero. Time period of Earth's rotation when weight of a body at equator becomes zero. That means body just fly off. Weight at equator means equal to zero means g dash at equator equal to zero. So we can say g minus r omega dash square equal to zero. Here I am writing omega dash because it is the new speed of new angular velocity of Earth's rotation. So we will get r omega dash square equal to g, omega dash square equal to g by r, then omega dash equal to root of g by r. This is the new angular velocity of Earth's rotation, and time period, new time period t dash equal to 2 pi by omega dash. So we will get t dash equal to what? 2 pi by root of g by r, or 2 pi root r by g. We know values of r and g, and by substituting those values we will get t dash equal to 84.3 minutes or 1.4 hours. 84.3 minutes and 1.4 hours. This time period is 1 by 17 times of 24 hours. 1 by 17 times of 24 hours. Then we can say if time period becomes 1 by 17 of the current time period t, then speed of rotation will be 17 times of the current speed. So that if the speed of rotation of Earth increases to 17 times of the present value, then time period of Earth's rotation will be 1.4 hours. It is around 1 by 17 of 24 hours. Then any body at equator feels weightlessness. Okay. Now, gravitational field, gravitational potential. Here you can see a mass capital M, and at a distance small r from the center there is a point P. Then what is the strength of gravitational field at that point? That strength is calculated by the equation I equal to, you can give capital E or capital I intensity of gravitational field or strength of gravitational field at point P is gravitational force acting per unit mass. Gravitational force acting per unit mass at the point. So we have to assume a unit mass at point P. Then we have to take the force acting per unit mass, force acting on the unit mass. Okay. F by m is actually gravitation acceleration due to gravity, force by mass. Okay, the small m mass is the mass we are assuming there at point P. Okay, so gravitational field intensity I equal to, we can say g, I equal to g, acceleration due to gravity. Here we can say only the magnitude of g. We can't take direction of g. G is positive or negative according to the motion of the body. Okay, if body is moving away from the body, if a mass small m is moving away from the capital mass M, its acceleration is negative retardation. For example, when a body is thrown vertically upward from the earth's surface, its acceleration due to gravity is negative due to retardation. When it is moving towards the earth, then its acceleration is positive. So acceleration due to gravity is positive or negative according to the condition of the body. If its speed increases, it is positive, and if its speed decreases, it is negative. But gravitational force of gravitation and gravitational field intensity, they are always negative, because gravitational field is attractive field. So I equal to, we can say, magnitude of G, and if you are taking the direction of force here, we will get I equal to what? Minus Gm by r square. If you are assuming a point mass m, then F equal to Gmm by r square divided by that mass m will cancel out. So gravitational field intensity equal to minus Gm by r square. Gravitational field intensity is negative because the gravitational field is attractive. Okay. Then what is the gravitational potential at that point? Gravitational potential is work done per unit mass. Work done to bring a unit mass from infinity, that means from out of the gravitational field to the point P. V equal to work done per unit mass, and for work done we can use the equation minus integral F dot dr by m. So we will get F by m is what? So V equal to minus integral I dot dr. That means if gravitational field intensity is given as a function of displacement, so to get the potential at that point, we have to integrate it with respect to dr and giving a negative sign. And from here we can say I equal to gravitational field intensity equal to minus dV by dr. Minus dV by dr, and if you are taking displacement as x, then you can say minus dV by dx. That means when you are differentiating the potential with respect to displacement and giving negative sign, you will get gravitational field intensity minus dV by dr. This dV by dr is called what? Gravitational potential gradient. Gravitational potential gradient. Like that you studied that electric field intensity equal to negative of electric potential gradient. Magnetic field intensity equal to negative of magnetic potential gradient. Like that here also we can say gravitational field intensity is negative of gravitational potential gradient. Okay. Differentiation and integration we always take when there is a function. When there is a function, that means the field is not uniform. In uniform gravitational field, in uniform not electric field, in uniform gravitational field, we can say what? I equal to minus V by R, or V equal to what? Minus IR. V equal to minus IR. This negative sign shows gravitational field is always attractive. So gravitational potential at a point P is found using the equation V equal to minus Gm by R. V equal to minus Gm by R. Okay, this negative indicates the field is attractive. Here you can see a question. The gravitational field due to a mass distribution is E equal to k by x cube in the x direction. K is a constant. Taking the gravitational potential to be 0 at infinity, its value at a distance x is, options are k by x, k by 2x, k by x square, k by 2x square. Just pause the video and try to solve it. Here E means gravitational field intensity. It is given as a function of xk by x cube. So from that we have to calculate gravitational potential. So V equal to what? Minus integral I dot dx, because function of x is given. Okay. Minus I is what? K by x cube dx minus integral k into x raised to minus 3 dx minus k into x raised to minus 3 plus 1 divided by minus 3 plus 1. So we will get what? Minus k into x raised to minus 2 by minus 2. Minus minus cancelled. We will get what? K by 2x square. This x raised to minus 2 will go to the denominator. So k by 2x square is the answer. Here you can see a table. Gravitational field intensity due to a hollow sphere and a solid sphere. Okay, inside, on the surface, outside, and at center, and graph between gravitational field intensity and distance small r. Okay, hollow sphere, solid sphere. Outside means distance greater than radius of the body. Gravitational field intensity equal to minus gm by r square. It is negative of acceleration due to gravity. That is why minus g dash h. Okay, and for solid sphere it is also minus g dash h. And on the surface I equal to minus g, because small r becomes capital R for both the spheres, hollow sphere and solid sphere. When we are taking conditions of Earth, we will always consider solid sphere. Then inside the hollow sphere there is no mass. Inside the hollow sphere there is no mass. So gravitational field intensity is 0. At the center also gravitational field intensity is 0. So we can say outside of hollow sphere gravitational field intensity is inversely proportional to r square. So you can see the graph. The graph is given in negative. Okay, because gravitational field intensity is negative. Okay, so you can say inside there is 0. Okay, inside there is nothing. Okay, A given in the graph as, instead of A you just take r, radius of Earth, and at surface it is minus gm by r square, and as distance increases from the surface it decreases minus gm by small r square. And you can see the case of solid sphere also. Inside it is I equal to minus g dash d, depth. Okay, due to depth, acceleration due to gravity is gm by r cube into small r, that we already discussed. So the shape of the graph will come in negative section. Inside it is directly proportional to r, and outside it is inversely proportional to 1 by r square. In the case of Earth, we always consider solid sphere. Now, what will be the gravitational potential due to hollow sphere and solid sphere? Next table. Outside, for hollow sphere and solid sphere, gravitational potential is minus gm by r, small r. And on the surface, minus gm by capital R. You can write capital Gm equal to small gr square, then we will get minus gr, small gr. Okay, and inside, for hollow sphere, inside gravitational potential is constant, same as at the surface. Okay, so we can say for hollow sphere, gravitational potential is same on the surface and at inside, everywhere, including at the center, and outside it is inversely proportional to small r, minus gm by r. So you can see shape of the graph there. The graph comes in negative section because it is always negative. So shape of the graph, you can see inside it is straight parallel up to surface, small r equal to capital R. Then it becomes hyperbolic because v proportional to 1 by r. And for solid sphere, that we will consider in the case of earth too. So it is important condition of solid sphere. You can see inside potential is given by minus gm by 2r cube into 3r square by small r square, where small r is the distance from the center of earth or from the center of solid sphere. So at center you can give small r equal to 0, then you will get minus 3 by 2 gm by capital R. And for gm by capital R you can give small gr, so you will get minus 3 by 2 gr. So you can say gravitational potential at the center of solid sphere is minus 3 by 2 into v surface, minus 3 by 2 into v surface. So you can see the graph there. At center it is minus 3 by 2 gm by r, and its magnitude decreases to minus gm by r as it reaches the surface, small r equal to capital R. Then again its magnitude decreases hyperbolically because it is proportional to 1 by r. Okay, here once more you think v center, gravitational potential at center is less than v inside, less than v surface, less than v outside. V center it is minus 3 by 2 gm by r. V inside we know the relation minus gm by 2r cube into 3r square minus small r square, it is v inside, and v surface is minus gm by capital R, and v outside is minus gm by small r. These are the equations we studied. So you can see there is a negative sign. That's why I am telling you, as distance increases from the center, gravitational potential increases. This negative sign is very important. So as distance from the center of earth increases, gravitational potential increases. That is why every body tends to move towards the center of earth, from higher potential to lower potential. Okay, that is why a person standing on a building tends to fall down towards the center of earth. Okay, because as height or distance from the center increases, gravitational potential increases, and its distance from the center decreases, gravitational potential decreases. Free movement of mass is always from higher potential to lower potential. Gravitational potential energy. We studied that potential equal to work done per unit mass. Then that work done is stored as potential energy of the body. So we can say gravitational potential energy equal to mass into gravitational potential. Mass into gravitational potential. Capital V is the gravitational potential due to earth or big body, okay, one body, and small m is the mass of another body. So for earth and a body of mass small m, or a planet and another body small m, we can say gravitational potential energy U equal to minus gmm by r, and between any bodies, gravitational potential energy equal to minus G m1 m2 by r, and for three bodies we can say there are three gravitational potential energy between m1 and m2, between m2 and m3, and between m1 and m3. So we can say minus G m1 m2 by r12 plus minus G m1 m3 by r13 plus minus G m2 m3 by r23. Here you have to listen that as distance from the center increases, magnitude of potential energy decreases. That means when we are not considering the negative sign, but actually potential energy increases. So we have to remember that as distance from the center of earth increases, gravitational potential energy increases. Negative sign has importance though. Here you can see one more table which shows gravitational potential energy of a mass small m due to hollow sphere and due to solid sphere. You can see on the top that U equal to m into V, mass into gravitational potential. So for hollow sphere at the surface it is minus gmm by small r, solid sphere it is also, and at the surface U equal to minus gmm by capital R. Minus gm by r is minus gr, so you can say it is minus mgr, and inside for hollow sphere it is minus mgr. But for solid sphere you have to use for potential the equation gm by 2r cube into 3r square minus small r square, and at the center of solid sphere minus 3 by 2 mgr or minus 3 by 2 gmm by capital R. For gmm by capital R we can use small m g capital R. Okay, next, when the separation between two bodies, is changed from R1 to R2, then work done equal to, we can say, change in potential energy. So minus G m1 m2 by R2, final potential energy, minus G m1 m2 by R1, final potential energy, minus initial potential energy. Minus of minus will become plus. So we can write G m1 m2 into 1 by r1 minus 1 by r2, because this minus 1 by r2 will be here it is 1 by plus 1 by r1, so 1 by r1 minus 1 by r2. For earth and another body system we can say work done equal to what? G into capital M small m into 1 by r1 minus 1 by r2. Here you have to take the distances r1 and r2 always from the center of the earth. If a body is raised from the surface to a height h, then what is r1? R1 will be capital R, because distance from the center we have to take, and at the height distance is capital R plus h. Then when we are applying this equation, work done or change in potential energy equal to Gmm into 1 by capital R minus 1 by R plus h. Gmm into R plus h minus R divided by R into R plus h. So we will get W equal to, work done equal to, this R we can take outside, Gmm by R into h by R plus h. Gmm by R into h by R plus h. This gmm by R you can write small mgr. into h by r plus h. Okay, gmm by capital R equal to mgr. Okay, now listen. Here, when I am taking again 1 r outside, work done W equal to gmm by r square into h by 1 plus h by r. Here there is no r, so when we are taking again one more r, I have to divide h with r. What is gmm by r square? It is gravitational force or weight of the body on the surface. So W equal to mg into h by 1 plus h by r. This equation we can apply when the body is raised from the surface to a height h. Now listen, if h is very less than r, if h is negligible when compared to r, then we can neglect h by r. We can neglect h by r, then what will we get? mgh by 1. That is, the work done is what? mgh. Or it is actually what? Change in potential energy. Change in potential energy. That means, we always discuss that when a body is raised to a height h, its potential energy is mgh. It is not actually the potential energy, it is the change in potential energy of a body when it is raised from the surface of earth to the height h. Then mgh is the extra potential energy of the body. Now, if the body is raised to a height h, where h equal to nr, then what will be the work done? W equal to mg into nr divided by 1 plus nr by r. R will be cancelled here. So we will get W equal to mgr into n by n plus 1. For mgr we can write gmm by capital R into n by n plus 1. This we can use if height h equal to nr, and if height is negligible, then only we can use this. Escape velocity. Escape velocity means the velocity given to a body to escape from the gravitational attraction of a planet or earth. For every body, binding energy, its binding energy equal to magnitude of gravitational potential energy. Due to the gravitational potential energy, every body is bounded to the earth. So, binding energy is actually magnitude of gravitational potential energy. So we can write gmm by small r, where capital M is the mass of earth and small m is the mass of the body. Okay. To escape, we have to give the body an energy which cancels this binding energy. So kinetic energy of the escaping body should be equal to gmm by r. Kinetic energy half mv square equal to gmm by small r. Small m we can cancel out, so we will get escape velocity v equal to what? Root of 2gm by small r. Root of 2gm by small r. Gm is here, gm is constant, so escape velocity we can say proportional to 1 by root r. Proportional to 1 by root r. To escape from the surface of earth, escape velocity should be equal to root of 2gm by capital R, that we will get root of 2gr. By giving the value, we will get 11.2 kilometer per second. 11.2 kilometer per second, and it is independent of mass of the body. Here capital M is only here, no small m. So it is independent of mass of body, it is independent of angle of projection theta. If it is given, if a body is given a velocity 11.2 km per second or velocity greater than it, it got an energy which opposes the gravitational potential energy. So it will escape from the gravitational pull of Earth. This velocity is also called second cosmic velocity. This velocity is also called second cosmic velocity. Kepler's laws, there are three laws. First law is called law of orbits. Law of orbits, that means every planet revolves around the sun in elliptical orbit with the sun at one of their foci. And second one is what? Law of areas. Law of areas. The line joining the sun and the planet sweeps out equal areas in equal intervals of time. The line joining sun and the planet sweeps out equal areas in equal intervals of time. Area by time is actually what? Areal velocity. So law of areas says areal velocity equal to constant, that is dA by dt. It is found using the equation L by 2m, where L is the angular momentum, of the planet. Here L you can give mvr by 2m, so we will get what? Vr by 2, and V equal to r omega, so you can give r omega, so r square omega by 2 also, or half omega r square, that is equal to dA by dt, areal velocity. If this is the elliptical path, this is the minor axis, and this is the major axis, with the sun at one of the focus, planet is revolving. If planet moves from A to B, time t1, in time t1, the line joining the planet and the sun covering area, that area I am giving as A1. Now, when the planet travels from C to D here in time t2, then the area line joining the planet and the sun covers area A2. According to law of areas, we can say if time t1 equal to t2, area A1 should be equal to A2. That is what discussed by law of areas. Line joining the sun and the planet sweeps out equal areas in equal intervals of time. So if t1 equal to t2, then A1 equal to A2. So we can say here the planet should have more distance, and here the planet should move small distance, because these areas should be same, right? So velocity of the body near to the sun will be large. Planet possesses higher speeds near to the sun, and planet possesses small speeds away from the sun. Velocity at perigee greater than velocity at apogee. Why? Perigee is the nearest point from the sun. Apogee is the farthest point from the sun. So we can say kinetic energy at perigee greater than kinetic energy of the planet at apogee. Angular momentum of the planet at perigee equal to angular momentum of the planet at apogee. Angular momentum is constant. There is no net external torque. dA by dt is constant. Mass is always constant. So L should be constant. Third law is law of periods. It states that square of time period of planet around the sun, square of time period of revolution of the planet around the sun is proportional to cube of semi-major axis. Here R is what? Semi-major axis. What does it mean? Semi-major axis means this is the major axis here. So this poses semi-major axis R, and here also R. This semi-major axis is found using R equal to R1 plus R2 by 2. What is R1? R1 means distance to perigee. Distance to perigee, and R2 equal to distance to apogee. From the sun, distance to apogee is R2 and distance to perigee is R1, and average of the distances is actually semi-major axis, half of the major axis. Satellite or planets revolving around the sun, or satellite revolving around the planet in circular orbits, then we will take this R as radius of the circular orbit. Orbital velocity of the satellite, VO. When satellite is revolving around the planet, the gravitational force between the satellite and the planet provides necessary centripetal force for the circulation, for the revolution. So we can say centripetal force for the satellite is given by the gravitational force. So mv square by r equal to gmm by r square. 1 r will cancel, small m, mass of the satellite is cancelled. So we will get orbital velocity equal to root of gm by small r. As radius of orbit increases, orbital velocity decreases. Root of gm by r. Okay. If the satellite is revolving very close to Earth's surface, the satellite is revolving very close to Earth's surface, small r we can give capital R, then we will get orbital velocity root of gm by capital R. This we can write root gr. Then we will get the value 7.9 kilometer per second. This is the velocity of satellite when it is revolving very close to Earth's surface. 7.9 kilometer per second. Here also we can say orbital velocity is independent of mass of the body. And this velocity is also called first cosmic velocity. First cosmic velocity. We got that escape velocity equal to root of 2 gm by small r. So comparing, we will get escape velocity equal to root 2 into orbital velocity. Okay, or we can say root 2 is 1.414 orbital velocity. So escape velocity equal to orbital velocity plus 0.414 orbital velocity. 1.414 we can write 1 plus 0.414. Orbital velocity plus 0.414, when we are converting into percentage, it will be what? 41.4% orbital velocity. That means what? If orbital velocity of a satellite increases 41.4%. If orbital velocity of a satellite increases 41.4%, then its velocity becomes escape velocity. That means it will escape out of the gravitational attraction. Time period of satellite. Time period equal to 2 pi by omega. We know that V equal to R omega, then omega equal to V by R, then 1 by omega equal to R by V, that is 2 pi R by V. For velocity we can give orbital velocity, then we will get 2 pi R by orbital velocity root of gm by R. R will go to the numerator. Inside there is a root R, so this R will go to the square root, R square into R. We will get time period T equal to what? 2 pi root R cube by gm. This is what actually told by Kepler's law, because T proportional to root R cube, then T square proportional to R cube. Okay, this is the time period of satellite. Okay, then this small r, at everywhere small r we can write capital R plus h. From there we can calculate height of the satellite too. Okay, now if the satellite is revolving very close to Earth's surface, we can give small r equal to capital R. Then we will get time period T equal to 2 pi root capital R cube by 4 gm. We can write small gr square. So we will get time period 2 pi root R by g. This value we already discussed, 84.3 minute or 1.4 hour. That means when a satellite is revolving very close to Earth's surface, whose time period of revolution will be 1.4 hour and whose speed will be 7.9 kilometer per second, that we already discussed. Energy of satellite. Kinetic energy equal to, we can say, half mv square. Here velocity is actually orbital velocity. So for orbital velocity our equation is root of gm by r. So gm by small r. So we will get kinetic energy equal to what? Gm m by 2r. Okay, kinetic energy is positive. Then as distance increases, kinetic energy decreases because its velocity decreases. Now, what is potential energy? Potential energy that we already discussed, minus gmm by small r. Minus gmm by small r. Then what will be total energy, total mechanical energy? Adding plus gmm by 2r minus gmm by 2r. This is actually half of gmm by r. So we will get minus gmm by 2r. Minus gmm by 2r. So by comparing these three energies, we can say total energy is negative of kinetic energy. It is half of potential energy. Total energy is negative of kinetic energy, half of potential energy. As radius of orbit increases, kinetic energy decreases, potential energy increases because of the negative sign, and total energy also increases. And total energy we can find, total energy is negative of kinetic energy and potential energy is potential energy is double of total energy. For example, if a satellite possesses 1 million joule kinetic energy, then whose potential energy is minus 20 million joule. Why? Potential energy equal to 2 into negative of kinetic energy, like that. So graph of kinetic energy will come in positive side and graph of potential energy and total energy will come on the negative side. energy, distance or radius of the orbit graph. You can see a table here. When orbit radius of satellite increases, orbital velocity decreases, time period increases, linear momentum, mass into velocity increases, angular momentum increases because angular momentum is mvr, and kinetic energy decreases, potential energy increases, total energy increases, binding energy decreases because binding energy is magnitude of total energy for a satellite. Listen, for a satellite, it possesses both kinetic energy and potential energy. So for a satellite, its binding energy is magnitude of total energy. Okay, and it is equal to, we already discussed, Gmm by 2r. To change the radius of the orbit, that means orbit changed and radius changes from r1 to r2, then work done should be change in total energy. Here satellite possesses both the kinetic energy and potential energy. Okay, in earlier case a body is moved from r1 to r2, that's what discussed, and that body was at rest. Here satellite is revolving around the planet, so it possesses both kinetic energy and potential energy, so work done should be total change in total energy. So we will get work done equal to what? Gmm by 2 into 1 by r1 minus 1 by r2, that is equal to change in kinetic energy, negative of change in kinetic energy, that is equal to change in potential energy by 2, because total energy is negative of kinetic energy and half of potential energy. Geostationary satellite which seems to be at rest with respective to a place from on the Earth's surface. So when a person observes geostationary satellite from that place, he will see the satellite is at rest because its time period of rotation is 24 hours and its sense of rotation is in its sense of revolution is in the sense of rotation of Earth about its own axis. So the satellite seems to be at rest, or relative velocity of geostationary satellite with respect to Earth is 0. So the orbit of geostationary satellite is called parking orbit. Orbit of geostationary satellite is called parking orbit. Okay. Orbital velocity of geostationary satellite is around 3.08 km per second, and height of geostationary satellite is around 36,000 km. 36,000 km. Sense of rotation of geostationary satellite is from east to west, and their height is around 36,000 km. But for polar satellites, their sense of rotation is from south to north or north to south, and their height is around 400 to 800 km. Small altitude satellites, they are polar satellites. Friends, this chapter gravitation is over here, finished. A material containing some entrance points, questions and the solutions is given in the description box that you can download, and when you are doing those questions you will get clear idea about the chapter and the next chapter we are going to discuss is mechanical properties of solids. Okay, keep going good, best of luck and stay safe.